So we are in causal inference and statistics. Geez, all the way up here. So it's this book right here, and we are on the last question of chapter 1, question 1.5.4. So here's the question. So define the structural model that corresponds to the Monty Hall problem, and use it to describe the joint distribution of all variables. Okay. So let's get into this. So hopefully you're familiar with the Monty Hall problem, and hopefully more still, you are familiar with how it is described in this book, but I'll give a brief paraphrasing of it right here. So the idea to the Monty Hall problem is that you're on a game show, and you're asked to pick from one of three doors. Okay. Now behind one of these doors is a car. Okay. And so we're going to call the door behind which there is a car Y. Okay, so this is a convention set up in the book. And then behind the two other doors are goats. So just something you don't want, I guess. Okay. So if you pick the car, you get the car. Okay. So you pick one of the doors, and the door that you pick we'll call X. Now, before you see what is behind the door you picked, door X, the host, whose name Monty Hall, that's why it's called the Monty Hall problem, opens one of the doors you didn't pick, and so we'll call the door that he didn't pick Z. Okay, and now inevitably it reveals a goat. Okay, because he's not going to show you what you picked, and he's not going to show you the car. That's why it's always going to be a goat when he shows you something. Okay, and so the Monty Hall problem says, so after he opens the door, he says, would you like to switch? And the question is, should you switch? This is the Monty Hall problem. Okay, so we'll kind of get into the answer, even though the question doesn't really ask for it. We'll give an explanation of the answer, but the answer is unintuitive. It's yes, you should always switch given this setup. Okay, and that's counterintuitive, and so that's probably why we're being asked to actually really think through this and model it. Okay, with our structural causal model. Okay. So here's what the model might look like. So we have our set of variables, x, y, z, which I've defined up here. And they have their own exogenous contributors, ux, uy, uz, just like we've seen earlier in the chapter. Okay. Now, the formula for x and y is just things that we can't model, u of x and u of y. Okay. In other words, the thing that you pick, there's no other variables in here that are explaining why you pick what you pick, and there's no variables explaining why they picked the door that they chose to put the car behind. Okay, but now Z, the door that Monty Hall opens, is a function of x and y as well as u of z. Okay, why is it a function of x and y? Well, again, it's because the host is not going to show you what's behind the door that you picked, and he's not going to show you the door that has the car behind it. So it's a function of x and y. Okay, so this is the structural causal model, and it would have a DAG that could look like this. Okay, so we have x leads to y, right? So x is contributing to y. So in other words, the door you pick influences what door Monty Hall shows you. The door behind which the car is hidden influences which door Monty Hall opens, and of course there's a random component to it here. Okay, and we'll see how all of these kind of play out. Okay, so again, what we're asked is, should we switch given the whole play out of of Monty Hall revealing one of the doors? Okay, so another way to say this is what is the probability that x equals y given z? In other words, what is the probability that the door that we picked initially is the door hiding the car, given that Monty Hall has revealed whatever door Monty Hall reveals? Okay. Now, if this value is greater than the probability that that we picked a door that does not conceal the car, okay. So again, if this probability is greater than this probability, then we should not switch, right? But if the probability that we have not picked the correct door, given what Monty Hall has revealed, is greater than the other probability, then we should switch. Okay, so that's how we can phrase this problem. So, so we're asking the question to give the joint probability distribution. Okay, well, the joint probability distribution is this, but we can decompose this, and we should, into this right here. Okay, so the probability of, so this decomposition reflects our causal model represented in this picture right here, right? So we have the probability of y not conditional on anything, okay? The probability of x not conditional on anything except for the ux, and we're ignoring that for now. And then the probability of z given y and x, right? And why is it conditional on y and x? Well, it's conditional on y and x because y and x are causal factors in determining z. Okay, so so again, you can kind of read this answer. It kind of discusses what I just put forward here, okay, in discussing the joint probability distribution. Okay, now really I think that's where the question ends, but I think that we should just carry this through to fruition. So we want to know, should we switch or not? Okay, we already know that the answer is yes, but let's just kind of continue. Okay, so now since each door is equally likely to be hiding the car, that probability is, for any given door, it's 1/3. Okay, and then similarly, we're equally likely to pick any of the 3 doors. Okay, and that's 1/3. Okay, so notice then that the probability of z given x and y means that z cannot equal x and cannot equal y. In other words, if I combine the probability that z equals x and z equals y, it's 0, right? Because Monty Hall will not open doors x or y. Okay? And so that means that when x does not equal y, right? So when x and y are 2 different doors, Monty Hall only has 1 door to open. Okay? In the case where x equals y, the host can choose from 2 doors, right? Because if x equals y, that only is one of the doors, and so he can pick from one of the 2 remaining doors. Okay? So in that case, there's a 50-50 chance of picking either of the remaining doors. Now the probability that x equals y is 1/3. And you can kind of do that math for yourself, but it's 1/3 that the door that we initially pick actually has the car. Okay, and so this means that 1/3 of the time you should not switch, right? Because 1/3 of the time you've picked the right one, and 2/3 of the time you should switch. Okay, so that means that we should always switch because 2/3 of the time we will be switching onto the correct door or to the door hiding the car. Okay, that's it.